Hi everyone, today we are going to learn about spacecraft thermal control subsystem. In this topic, you will learn about spacecraft thermal control system, and at the end of this class, you should be able to list the primary sources of heat for spacecraft, to describe the three basic means of heat transfer: conduction, convection, and radiation, and how to use them on spacecraft, to describe the various ways to control heat outside and inside a spacecraft, and to explain how the thermal control device operate. As our objective, number one, to maintain all the components within the allowable temperature, and you will understand that every single component inside the spacecraft have their own operational temperature. To guarantee the optimal performance of a component in operational condition, to avoid damage in non-operational condition. Number 4, to guarantee temperature stability for optics, optomechanical devices, or any component sensitive to temperature, especially sensors. Number 5, to identify the relevant parameter and those with high influence on the thermal behavior of the spacecraft and manage them with the existing constraint given by the environmental condition and the spacecraft resources. Number 6, to guarantee the interface. As an example, the spacecraft instrument requirement, temperature, and heat flux are met. And number 7, to minimize the temperature gradient according to the specific limits. This is the typical thermal requirement for spacecraft components. Here, the most important component is battery. The thermal control system is mainly to ensure the temperature is minimal for battery to well function. Today we are going to learn about the spacecraft thermal environment. Typically, the biggest problem for spacecraft thermal control is removing heat. For the most part, we must maintain temperature inside even unmanned spacecraft at normal room temperature, which is 20 degree. In some cases, specific payload may have more demanding requirement. Infrared sensor, for example, require refrigeration unit to supercool them to minus 193 degree. This figure shows heat in space come from the three main sources: the sun, the earth, and internal sources. Near Earth, the biggest source of heat for orbiting spacecraft is the sun, about 1,350 watt per meter square. As we live in Malaysia, we all know how hot is the scorching sun. For a satellite in space, the sun heat is much more intense because there is no atmosphere to absorb radiant energy and moderate the temperature. On the side facing the sun, the surface of a spacecraft can reach many hundreds of degrees Kelvin. On the side away from the sun, the temperature can plunge to a few degrees Kelvin. And the solar constant is the amount of incoming solar radiation per unit area measured on the outer surface of Earth's atmosphere in a plane perpendicular to the ray. So, summer solstice is the moment during the year when the path of the sun in the sky is farthest north in the northern atmosphere, approximately during on June 20 or 21, or farthest south in the southern hemisphere. The uh, which is the day has the most daylight. Winter solstice happens when the North Pole is tilted furthest away from the Sun as the Earth continues on its orbit, which is why it is the winter. Uh, this it is winter the northern hemisphere at this of the year. In the southern hemisphere, it is exactly the opposite story. The South Pole is pointing toward the Sun, making the summertime in Australia. And the solar radiation is a radiant or electromagnetic energy from the sun. The three relevant bands or range along the solar radiation spectrum are ultraviolet, visible and infrared. Of the light that reach Earth's surface, infrared radiation makes up 49 percentage of visible light, provide of 43.9, while visible light provide for 42 percentage. The ultraviolet radiation make up just over 8% of the total solar radiation. Each of these bands has a different impact on the environment. Solar irradiance is the intensity with which radiation enter Earth's atmosphere. An relatable way to think about solar irradiance is by looking at the difference between a 20-watt light bulb and a 100-watt light bulb. Both produce visible light in the same wavelength, but the brightness and intensity are very different. The 100-watt bulb have a higher intensity or irradiance. Solar irradiance is the amount of radiant flux on an area and is measured in watts per meter squared. This is the equation to show solar radiation intensity at any distance, while P is the total power output from the sun. Scientists use the term albedo to describe the percentage of the solar radiation reflected back into the space by an object or surface. A perfectly black surface has an albedo of 0, all radiation is absorbed. A perfectly white surface has albedo of 1, all radiation is reflected. Earth average albedo is about 0.3. In other words, about 30% of incoming solar radiation is reflected back into space and 70% is absorbed. When object reflect most of the light that hit, it looks bright and it has a high albedo. As example, snow, light roof, and water. When object absorb most of the light that hit, it look dark, and dark objects have low albedo such as forest, dark roof, and asphalt. This is a visibility factor or F and albedo value for the planet in solar system. A sensor aboard NASA Terra satellite collecting detailed measurement of how much sunlight of Earth's surface reflect back into the atmosphere. By quantifying precisely our planet albedo, the Moderate Resolution Imaging Spectroradiometer or MODIS is helping scientists understand and predict how various surface features influence both short-term weather pattern as well as longer-term climate trend. The color in this image emphasizes the albedo over the Earth's land surface, ranging from 0 to 0.4. Areas colored red show the brightest, most reflective region, and yellow and green are intermediate value, and blue and violet show relatively dark surface. White indicate where no data were available and no albedo data are provided over the ocean. Infrared radiation or infrared light is a type of radio energy that is invisible to human eye but we can feel as heat. All objects in the universe emit some level of infrared radiation or IR radiation, but two of the most obvious sources are the sun and fire. So the highest value of Earth emitted IR will occur in tropical and desert region. The amount of radiation received by the Earth varies and much of it is reflected back into the atmosphere. This map shows net absorbed solar radiation. And the NASA Atmospheric Infrared Sounder instrument aboard sends emitted infrared and microwave radiation from Earth to provide a three-dimensional look at Earth weather and climate. The illustration shows temperature at an altitude about 10,000 to 50,000 feet above the ground. The lowest temperature are shown in purple and blue and range from minus 40 degree Fahrenheit to minus 10 degree Fahrenheit. And Another source of the heat is free molecular heating. This type of environmental heating is caused by the bombardment of the spacecraft by individual molecules. This is the reason why this phenomenon only occurs when the spacecraft is placed in the outer part of the atmosphere at the end of the launching phase, after the booster payload fairing is ejected or during re-entry. And in space, there are two types of radiation, ionizing and non-ionizing radiation. The first one has enough energy to remove electrons from the orbit of atom, resulting in charged particle. The interaction with this charged particle heats up the spacecraft. In other words, the interaction with charged particles that are caused by ionizing radiation cause the spacecraft to heat up. Nevertheless, it is weaker than the previous heating source, being significant just in cryogenic temperature, where sensitive systems may be affected by this heat load. For example, in the Van Allen belt region, there are several trapped charged particles which can modify the temperature of the satellite. The Van Allen probe, formerly known as the Radiation Belt Storm Probe, will study two extreme and dynamic regions of space known as the Van Allen radiation. Van Allen radiation belt that surround Earth. Named for their discoverer, James Van Allen, these two concentric donut-shaped rings are filled with high-energy particles that gyrate, bounce, and drift through the region, sometimes shooting down the Earth's atmosphere and sometimes escaping out into space. The radiation belt swell and shrink over time as part of a much larger space weather, larger space weather system driven by energy and material that erupt off the sun's surface and fill the entire solar system. That's all. Thank you.